Welcome to TNO's Materials Solutions Research Group at the High-Tech campus in Eindhoven and the Brightlands Chemelot campus in Geleen. The development of materials plays a crucial role in achieving the Sustainable Development Goals. We develop materials that facilitate and accelerate the transition towards a sustainable society. Easy to recycle, smart functionality, energy saving, low environmental footprint, and significantly reduced critical or toxic substances to create a resilient infrastructure and sustainable industrialization. In our facilities, we perform material synthesis, characterization, processing, and performance validation, directly connected to the application domains we are active in. Sustainable buildings, energy conversion and storage, sustainable mobility, circular packaging, and polymer solutions. In our laboratories, we prepare and apply materials at both lab and pilot scale. This is nicely illustrated by the development of our thermochromic SunSmart coatings for smart windows, which starts with the chemical synthesis of an organometallic vanadium complex in a multi-litre batch reactor, followed by controlled thermal anneal in a rotating tube furnace operated under inert gas atmosphere. The resulting vanadium dioxide powder is subsequently milled to produce nano-sized pigments used in the coating liquid. Subsequently, the coating is applied to the surface of glass and cured in our pilot production line for functional coatings. Advanced characterization techniques are used to assess the quality of the coating and its components, including thermogravimetric analyses, differential scanning calorimetry, and temperature-controlled UV-Vis-NIR spectroscopy. We also develop inorganic materials for photocatalysis and photoelectrocatalysis, including plasmonic nanocatalysts for sunlight-powered CO2 conversion and semiconductive photoelectrodes for production of green hydrogen. To validate the performance of these materials, we developed tailored batch and continuous flow photoreactors. In these reactors, we study the light-powered conversion of CO2 to syngas or methanol as function of irradiance, pressure and temperature, and the light-powered production of green hydrogen by photo-water splitting. In addition to developing inorganic materials and coating, we are experienced in polymer processing. We operate pilot-scale equipment such as the thermoplastic composite recycling pilot line. In this pilot line, we convert production waste from polymer composite manufacturing and end-of-life polymer composite products into high-performance secondary raw materials for structural parts. The pilot line has a flexible setup, can operate at high throughput, and is able to process a wide spectrum of material types and shapes. Use of the recycled materials is validated in different production processes, such as injection molding, overmolding, and 3D printing. We apply 3D printing of continuous fiber composites with high strength-to-weight ratio. For example, for the production of structural parts for drones and small aircraft, where weight reduction is essential. We develop dedicated printing setups and design methodologies to fully exploit the functionality of continuous fibers in the end product performance. Our expertise in functional polymer design and processing is applied in the development and production of post-consumer recycled-based polymer films for circular packaging solutions. With our polymer compounding, film extrusion, and injection molding equipment, we develop and validate new recyclable packaging designs based on post-consumer recyclate. We also improve the sealing performance of flexible packaging, often a key issue in the development of new sustainable packaging designs. This is supported with an in-house developed machine learning sealing model. In specific cases, we combine our knowledge in inorganic and polymeric materials. A good example of this is the development of PFAS-free fire-extinguishing foams, which are based on synergistic action of polymers and inorganic nanoparticles to trap water in polymer lamellae and achieve the desired performance. Ensuring and predicting the quality of plastics during processing, use and recycling is an important way to improve the circularity of plastics. This is particularly relevant for plastics that are exposed to high temperatures or UV light. For example, we perform accelerated UV aging tests and monitor the deterioration of the plastic properties by several characterization techniques, such as tensile testing, nano-indentation, Raman and FTIR spectroscopy to reveal the changes in chemistry and mechanical properties. A second example of plastic performance and quality is the research on the formation of microplastics. Not only do we gain insight in the mechanisms of formation, but we have used this knowledge to produce reference microplastics of various types of plastics by milling, grinding and sieving, followed by a detailed characterization. This resulted in many reference microplastic particles that have been used in the large Dutch microplastic program, Momentum. All materials we develop are extensively characterized, from electron microscopy to study the size and shape of inorganic particles, to spectroscopy to assess the chemical composition, and nano-indentation to determine the mechanical performance of thin films and polymers. In specific cases, we participate in the development of new characterization tools. For example, for real-time monitoring of particle size and concentration during bead milling of ceramic powders, and for operando monitoring of catalytic processes. Latter techniques involve operando infrared spectroscopy and operando temperature measurements at multiple positions inside illuminated catalyst beds. All these facilities support our 5 application domains, ranging from photocatalysts and photoelectrodes to monomaterial retortable soup pouches. With our knowledge, facilities and partnerships, we create material solutions that help industry transition towards sustainability and move society forward.